PageRank tells you who is important. Node2Vec tells you who is similar. This is the workflow you'll know how to run when we're done, which learns node embeddings from a graph and returns the most similar nodes for a given node. I'm Professor Pi, teaching AI foundations with simple Python. Graphs are everywhere. Social networks, product co-purchases, knowledge graphs. The common need is not just who is central, but who is similar. Node2Vec turns nodes into compact vectors, so similarity becomes a geometric query. Practitioners use this for recommendations, candidate generation, or bootstrapping classifiers. It works well on small to medium graphs where a few dozen to a few thousand nodes fit in memory, and it gives you a numeric feature you can reuse across models. At a high level, Node2Vec runs many short random walks through the network and treats those walks like sentences. Nodes that appear in similar walk contexts end up with similar vectors. The trick is biasing walks to capture community structure or role similarity. This makes it flexible. Strong point is simple downstream use. Weak point is tuning the walk bias and vector size. We will build a tiny example you can follow in minutes. First, we make a small 8-node graph to see the shape. Then we run Node2Vec to learn 8-dimensional embeddings. Next, we query the most similar neighbors for node A. Then we change walk bias to watch the neighborhood change. Finally, we use the embeddings to assign A to one of two teams by centroid similarity. This keeps the code readable and shows the full practical flow before any scaling. Now, we create the toy graph and inspect its basic structure. This snippet builds a small NetworkX graph you can read at a glance and checks a simple structural fact. We define a list of edges connecting 8 nodes into 2 lightly connected regions. Then create the graph object G and add those edges. The variable deg_a queries how many neighbors node A has, and n counts the total nodes so you know the graph's size. This gives a quick feel for the network shape without any embedding yet. Degree is easy to compute, but doesn't capture nuanced similarity, which motivates learning embeddings next. The printed values confirm the graph size and that A connects to 3 neighbors. Running this first makes the later embedding behavior easier to interpret. Next, we fit Node2Vec to collect embeddings from those random walk contexts. This example trains Node2Vec on the same NetworkX graph to turn nodes into vectors you can use downstream. The Node2Vec object runs biased random walks over G using dimensions equals 8 for compact vectors, walk length equals 10, and num walks equals 20 to gather contexts, and P over Q at 1.0 for neutral bias. Calling fit returns a gensim model. Its model.wv holds the learned embeddings keyed by node ID. We read the vector length for A as dims and the trained vocabulary size as trained. Increasing dimensions usually improves expressiveness at a higher compute cost. More walks and longer walks often stabilize quality, but add time. The print confirms we embedded all nodes at the requested dimensionality. Now we use those vectors to find similar nodes to A. This code queries the Node2Vec model to retrieve the nearest neighbors of node A by cosine similarity. The method most similar returns a list of tuples where each pair holds a neighbor ID and a similarity score. We collect the node IDs into names for readability and take the first one as the top match. This is the core retrieval operation you'll reuse for search, recommendations, or candidate generation. If you raise top n, you'll see a broader neighborhood. If you reduce it, you focus on only the strongest match. The printed node is the most similar peer to A under the learned embedding. Next, we change the walk bias and retrain to observe how recommendations shift. This example retrains Node2Vec with different walk biases to show how similarity can shift. We set P equals 4.0 to discourage immediate backtracking, and Q equals 0.5 to emphasize BFS-like local exploration. Together, they skew contexts toward closer neighborhoods. After fitting, we take the top 3 similar nodes to A from the original model and the new model, then compare the sets. The variable changed is true if the recommended neighbors differ, which signals that tuning P and Q affects what the model deems similar. Lower Q tends to prefer tight local communities. Higher Q explores outward more, like DFS. The printed flag tells you the top 3 recommendations actually moved. Finally, we convert embeddings into a tiny classifier. Which team does A belong to? This snippet uses Node2Vec embeddings for a tiny nearest centroid classifier that assigns A to a team. We define 2 small labeled groups. Then centroid computes each team's mean embedding using model.wv vectors. The function cos is a plain cosine similarity to compare A against each centroid. We choose the label whose centroid is closer to A in embedding space, which turns network structure into a simple, usable feature for downstream tasks. Adding more labeled examples usually sharpens centroids. If your teams overlap, consider increasing walk length or dimensions first. The printed label shows which group A most resembles under the learned representation. This toy pipeline maps directly to real problems. In a product graph, you would embed items, retrieve nearest neighbors as candidates, then re-rank with business features. In a social graph, you would find similar users for follow suggestions. The steps scale the same way. Larger graphs need more walks or subsampling, and an approximate nearest neighbor index for fast queries. Recap. What it is, Node2Vec learns node embeddings by biased random walks, so similar nodes sit near each other in vector space. When to use it? Use it when you need fast similarity queries, candidate generation, or simple features from graph structure. One caveat. Results depend on walk bias and vector size, so tune P, Q, and dimensions for your signal. Next step. Tune the walk bias parameters P and Q and compare top K neighbors as you change them. Watching how recommendations drift is the fastest way to learn what those knobs actually do on your graph. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.